Okay, cool. Let's start. We'll cover a lot of things, but without getting too deep into the problem. There's lots of different stuff there, but please send your questions into the Q&A thing. I'll be happy to answer them and talk in more detail about various aspects of the problem. Okay, short about me. My name is Mikhail Samin. I'm the CEO at OGD. We're the leading B2B music recognition company. We have lots of things with machine learning inside, and I'm excited about the line problem. And I think there's lots of implications in both in the near term and in the long term for machine learning and for the future of AI. And I'm excited to talk about it. Feel free to email me afterwards. My email is ms@contact.ms. And again, please send your questions to the Q&A thing. I'll briefly explain how modern machine learning works, and then I'll talk about outer element problems, which is a nice separation of the problem into something that's about currently specifying objectives that you want your systems to pursue, and finding the right Mesa-optimizers. I'll talk about what they are later. I'll also talk about potential solutions to this problem, and I'll talk about what problem arises as AI systems get generally capable. Okay, a bit of background. Some people work on data science. Some people just start learning about AI. 20 years ago, problems that I'm going to talk about were already predicted, but I'm going to talk about the line problem in the context of modern machine learning. So a bit of background. Most of modern machine learning is deep learning. So if you have any algorithm or any function, we have nice theorems that say that there are neural networks that can approximate these functions or algorithms sufficiently well. And what we do is we just take some nice neural network architecture and we look for weights for this neural network such that it performs well on some function that we use to measure its performance. And this way, with gradient descent for parameters or for neural network, we can find algorithms and functions that perform well on some function. That works really well, and this is what most of modern machine learning is. Okay, now to the problems. Outer element is basically about how do you make sure that the thing you're optimizing for represents what you actually want the system to do. So you have some function that you use to measure the performance, and how do you make sure that scoring high on this function is something that you actually want. This is surprisingly complicated in systems that are smarter, but I think some examples from just like life or history or mythology can be helpful. So, for example, in Greek mythology, there's King Midas who wished for a golden touch, and his wish was granted. And he didn't realize before that what he wanted isn't just to turn everything into gold. He also wanted to eat and to be able to like touch food and other things. And this difference between what he wished for and what he got, between what he wished for and what he actually wanted, led to catastrophic consequences for him. In reinforcement learning, we don't yet get any catastrophic consequences, but the difference is still something that leads to the things that we wouldn't want. So, for example, this is a game called Cost Runners. OpenAI trained an agent to get a high reward in this game. So the score in the game was basically the reward. And they wanted the agent that they trained to just complete the game. And what they got is an agent that's not just a nice circle where it could run around, collecting these green boosters that gave a lot of score and never complete the game. this is what's called reward hacking, when there's a difference between the reward that you specified and what you wanted, and this difference is exploited by these agents. Okay, what can be done about this? One nice solution is what's called reinforcement learning from human feedback, or RLHF. In particular, it's used for ChatGPT, a language model created by OpenAI. It is a way to specify the reward. Instead of just specifying some function that takes in the environment or some kind of state and output the reward, instead you train a reward model, something that predicts what feedback a human would give to the behavior of your policy. And this is actually pretty nice. It allows you to extract human preferences. And then when you have this reward model, you train a policy that optimizes for the rewards that this model predicts a human would give. So you just train a thing that basically says how well a human would react to something that you output, and then you train the system to output what a human would react to nicely. And this works pretty well. ChatGPT exploited and it's like really useful and helpful in comparing to even smarter, but smarter models that were harder to actually use and that weren't trying to be helpful and harmless, etc. Unfortunately, reinforcement learning from human feedback also fails as systems have more optimization power, because what preferences humans reveal and what they actually want is also different. For example, a couple of years ago, they trained an agent to pick up things, just do things in the environment. And the objective here was to pick up the ball, and examples of picking up the ball. Oh, sorry, I should probably say one more thing about RLHF. Yeah, so like it's really efficient. You can train a robot to perform a backflip by showing only 40 examples of different behavior to humans. So you show 2 examples to a human, and they say whether it looks, which one looks more like a backflip. And after 40 bits of information, the robot is trying to do backflips. Yeah, so here it was trying to pick up the ball. And what it actually did is just hovering between the ball and the camera. So human writers who looked at this thought that it was successful doing the task, but it wasn't. It was just, it was able to find a way to exploit the difference between what humans actually wanted and what was easier to do, because you can just hover between, and the humans don't see the full 3D environment, they just see pictures from the camera. So this is what the agent did instead. A couple of more fun things. I asked ChatGPT what RLHF is, and it answered that it doesn't know. And when I asked it what reinforcement learning from human feedback is, it answered not that well, but it even gave the example when I asked how it fails. It even gave the example that I showed you before with the robot arm hovering it between the camera and the ball it was supposed to pick up. So even though it doesn't understand exactly what's going on with the robot arm example, it's still aware of what RLHF is. But humans or human writers were evaluating, saying, I don't know, better than bad sounding explanations that they didn't really understand. And they were evaluating giving a good sounding explanation better than saying, I don't know. And that means that if you can lie and give a good sounding explanation that a human writer wouldn't find issues with, you just do that. because it's something that gives you more points. It's something that your reward model predicts that humans would evaluate better. It might be easier to look at a model fine-tuned with RLHF, like ChatGPT, and think that it has converged to something that's actually helpful and harmless. Instead, it might be better to consider something like training alien brains to predict next words of human texts, and then become more goal-oriented and for a smaller face. This is a meme from Twitter, a depiction of alien minds being fine-tuned with RLHF. This is what a lot of scientists, including people working at OpenAI, DeepMind, think these text models fine-tuned with RLHF look like. So yeah, you aren't exactly able to make a thing that actually wants to be helpful and harmless. You just specify something that looks nice on the outside, but you have no idea what's going on inside of it. Yeah. I'm not sure I have time for. Yeah, probably do. Okay. As models are deployed on increasingly complex tasks and become increasingly capable at word hacking, you'll get dynamics that if the model intentionally has this ability to understand what's going on and what interface it uses to interact with the world, that it is a machine learning system, that humans are writing its behavior and will respond somehow. It will be able to, by having just some goals, no matter like how, no matter how aligned they are with ours, exploit this knowledge and output things that humans would evaluate better. And so gradient descent will steer towards models that are just understand what's going on and are able to output things that humans think are nice, but like not for the reasons of being nice or helpful. Essentially, our model might carry out word hacking, by example, for example, by choosing actions that exploit biases and blind spots in humans or learned through word models. This might involve matching its answers to the supervisor's stated views, regardless of truth, a behavior that actually emerges in language models trained with RLHF. It can use detectable distribution shifts to recognize whether it's currently being trained in the real world on or on offline data or in a simulated environment. And it can use this understanding to understand what behavior will be penalized and only misbehave when it knows that there's no loss of reward in that case. It can identify which lies could be caught by existing interpretability tools. I'll talk about what it is a bit later, and only give answers that cannot be shown false by these tools. This is also a problem that was kind of predicted many years ago. I think more than 20, maybe 21, 22. There was a paper on digital organisms which were trained with genetic algorithms. They evolved to recognize when they were being evaluated, and they ceased unwanted behaviors only to continue them once evaluation ended. Okay, a couple more things about the outer line problem. One question that people often ask is why wouldn't these models just be nicer to us when they're smarter? Like when human children grow as it grows, they usually become more prosocial and everything. And the answer to this is so-called orthogonality thesis. It was suggested by Nick Bostrom, and basically notices that for any set of goals, there is an algorithm that can optimize the feature of the universe for these goals sufficiently well. And you can imagine that there are two axes. One is what goals you have, and another is how smart you are, how capable you are. And there are algorithms that for any set of goals can be as smart as like any kind of smart. And because of that, you can train an agent to be smarter and smarter, and it at no point it will just change its goals to be something that's more aligned with you. If your reward function doesn't incentivize aligned behavior, there's no reason to expect that it will just emerge out of nowhere, even when your reward function incentivizes something else. Another related thing is can't we just turn it off if it does something wrong? Like what the problems are? And so to answer us first is at like sure at the current level of AI capabilities, even though a Bing chatbot can threaten users, it's not that bad. It's not that important, and it doesn't lead to catastrophic consequences usually. Even though I don't know, like people's preferences can be changed by YouTube and Facebook algorithms because they just optimize for something a bit different from what users would want. But yeah, a more important problem is so-called convergent instrumental subgoals. It is a set of things that any smart agent would try to do, no matter what their goals are. For example, as Stuart Russell, a researcher, puts it, you can't fetch coffee if you're dead. You can imagine a robot that has a goal of fetching a coffee, and it's its only goal. And the problem is, if you try to switch it off, it will be trying to prevent it because it will not be able to fetch the coffee if it's dead. Other things are preserving its goals, because if the future version of you has some different goals from you, then your current goals will not get maximized. So for example, if you want to maximize the amount of smiley faces in the universe, and you know that if you do some mistake, a future version of you will maximize the amount of paperclips in the universe, you'll try to prevent that, because if the future version optimizes for the amount of paperclips, there will not be as many smiley faces. Also, you'll try to acquire resources and become smarter, because both of the things allow you to achieve your goals better, and these are also converted instrument samples. Okay, let's go to the neural element, Mesa-optimizers and stuff. So another problem is that even if you have a reward function that represents what you actually want pretty well, it's really hard to find agents that actually try to optimize this for this function and not something else. Because actually, when you just start training, what you get first is just some collection of heuristics that perform well in a function. Like, I don't know, if you see a monster in a game, avoid it, or like jump over the obstacle. But agents that have some inner goals that try to achieve something intentionally perform a lot better on a wide range of tasks. And so after a set of heuristics, you'll start finding agents that actually have some goals of their own. And the problem is, even if the goals are not exactly what the reward function is looking for, if they correlate well enough on the training distribution, these agents might still be selected by gradient descent. So, for example, there's a game called Coin Run. People trained an agent to complete the game. At the end of every level in the game, there was a coin, and they were giving reward for collecting points in that game. So originally, agents were trained to just find coins, but they were always on the right side of the level. What they found instead was an agent that was trying to get to the right side of the level and didn't really care as much about coins. What's caring about coins and caring about getting to the end of the level are goals that are that having them produce reward. But out of the training distribution, if you moved the coin from the end of the level to some other location, the agent just didn't care about it, even though it was something that was giving you reward. Yeah. As AI systems get more capable, a wider variety of goals lead to behaviors that achieve high rewards. So if you, whatever your goals are, if you're really smart, you can imagine that you will just play a game for instrumental reasons, because like if you don't achieve a high reward in the game, you know that you will get changed. Guardian Descent will steer from your goals and your algorithms that you're implementing, and so you will try to achieve high reward intentionally. Another thing is, even if you're not that smart, there's just like many things that many goals that correlate with what reward function measures. And if you have a difference between what goals of this Mesa-optimizers of agents are and what you want, it doesn't really matter that like on the training distribution they were pretty correlated. Out of the training distribution, you might start getting something that you don't want. Okay, we are running out of time. I'll probably skip. Okay, one thing I'll tell about this. So with large language models such as GPT-3 or Palm or upcoming GPT-4, is that they are trying to predict only the next token, or you can think about this as the next word in a text. And this means that you're actually avoiding optimization pressures towards having goals. So a model that doesn't have any goals, it just predicts the next word in the text, gets a reward that's as high as a model that tries to do something and for these reasons tries to predict the next token well. So you can think about large language models as myopic. They aren't really trying to do anything in the long term. Unfortunately, it breaks if you add any form of throttle turning or introduce other optimization pressures, such as just putting the tokens that it outputted as its new inputs. Okay. Not sure I can. Yeah. People at DeepMind and OpenAI work on creating an AGI. They understand that the line problem is actually a global catastrophic risk, but they unfortunately don't have a specific plan for solving it. It's a large problem with many things around it. There are some ways to solve it, but the general problem is that it is really hard to point at minds. If you imagine the space of all possible weights of a neural network or all possible artificial general intelligences, there are some areas in the space that are aligned, but unless you're able to specify what exactly does it mean for these things to be aligned and how do you get there, it is something like you're trying to launch a rocket to the moon. You have a lot of explosives, but you don't have equations for gravity, and you don't know where exactly moon is, and like maybe you have only some initial understanding of, I don't know, acceleration. Yeah, uh, you can try to what's different from humans is that in artificial neural networks, you can actually look at the weights, and so you can try to understand what the model are thinking about, what the goals are, but by just like looking at the circuits of activations that the goals are. But unfortunately, in those, there's like some general program that can look at any neural network and tell whether it's aligned and what its goals are. It's probably really hard to get to that kind of program, and I'm not sure it's possible in the times that in the maybe years or decades that are left before AGI happens. Yeah, if the systems are not too capable, it's probably possible to just do response learning from human feedback to extract preferences from humans, or you can just think about what you're optimizing for, what are the incentives that create the agents, and what distribution shifts might exist, and this can also help. Okay. Um, um, Additional resources. If you're interested in potentially working on this problem, um, it is something that's probably highly impactful in terms of just benefiting humanity, because as systems get more capable, this problem gets worse and more serious, and the consequences of not solving this problem can be pretty catastrophic. So I recommend a problem profile on artificial intelligence from an Oxford nonprofit called 80,000 Hours that works on discovering what are the most uh, pressing problems humanity faces. Another thing is AGI sexual analysis. It is a free course from people at Cambridge on AGI safety and the alignment problem. And also alignmentforum.org is a website with lots of resources on the problem as well. Okay, and now I'll be happy to answer your questions. Sorry, I skipped over a bunch of stuff, but I was running out of time. You can ask questions via the Q&A thing. Yeah. Okay, I can probably just like come back to. Do I want to? Okay, yeah, I'll just listen for questions. Okay, if there are no questions, I can wrap it up. Feel free to email me at ms@contact.ms or DM me on Twitter. Yep. Thanks, everyone.
Thank you. Bye.
Bye.
Thank you. Greetings from Peru. Bye.
South Africa.
I'd say as there's a question on where to start in order to develop well in the field. I'd say just try to find some problems you want to solve and then just use the power of the internet to find out how to solve this. It is probably the best way to develop skills in any sort of IT field, including deep learning. Yeah.